Hello, this is our second lecture on magnetic resonance imaging. After today's lecture, students will know about the static magnetic field B0 and the magnetic field B1 generated by the radio frequency transmit and receive system. Students will learn about gradient fields needed for localization and Shimming coils used for magnetic homogeneity. Students will also learn about various radio frequency coils. A complete module of the MRI system is shown on this slide. The system is made up of the main magnet that generates the static B0 field. There is also a B1 field generated by the RF transmit coils. We also have the gradient coils used for localization. The system also has various Shimming coils used for homogeneity corrections for the main static magnetic field. The main magnet, the gradients, the transmit and receive coils, and Shimming coils are all connected to power supplies. A pulse generator is used to create the RF pulses needed for excitation, and computers are used for data storage, processing, and display. Let's look in detail at the main static magnet. Hospital MRI magnets are either made of air cores, solid cores, or superconducting cores. Air core and solid core resistive magnets are usually low Tesla magnets of about 0.3 Tesla. These do not require the use of helium for cooling and so are cheaper to operate. Because these magnets rely on room temperature resistive coils to generate the magnetic field, the field strengths are limited because of the limited currents generated in resistive coils. The top image on the slide shows the coils in a resistive coil magnet. The bottom image shows a commercial magnet made from resistive coils. Higher field strength magnets are made from superconducting coils. Superconducting coils require liquid helium and liquid nitrogen coolants to keep the coils cold enough for superconductivity. These magnets can generate higher field strengths of 1.5 Tesla or above and are more expensive to operate. The top image on the slide shows a commercial 1.5 Tesla superconducting magnet, and the bottom image is a cutout of coil layouts of a superconducting magnet showing locations of the various components. The next MRI component is the gradient. Gradients are added to the main B0 field to generate different slice locations and thicknesses. There are three types of gradients: the slice select gradient, the phase encoding gradient, and the frequency encoding gradient. We shall learn more about these shortly. Image slice locations are determined by frequency and phase information of these gradients. The left figure shows the orientation of the gradients relative to the subject to be imaged. On the right image, two gradient coils are shown with the distribution of the magnetic field between the coils. The fields add up in the area between the coils to generate a uniform gradient. The gradient field shown on the previous slide is shown here without the coils. It has a null point about which the gradient causes a net decrease or increase of the field strength of the main magnet. If there is a net increase, protons precess at higher frequency, and if there is a net decrease, protons precess at lower frequency. These precessional frequency differences are used to localize the positions of protons relative to the main magnet field, essentially localizing their position in a slice. The top image shows the gradient coils within the main magnet setup. If all three gradients are activated, the net gradient is a vector sum of the three gradients. The next component is the Shimming coil. Shimming coils are used to adjust the homogeneity of the magnetic field. There are two types of shimming: passive and active shimming. Active shimming adjusts the magnetic field by using currents through the shim coils, while passive shimming involves inserting pieces of metal at points in the magnet to adjust the homogeneity of the field. We shall look next at an important component of MRI, the radio frequency coils and system. The radio frequency system is made up of the radio frequency pulse generators and coils that can both transmit and receive radio signals. The transmit-receive feature can be combined into a single coil. The next few slides will examine the radio frequency system and the coils. For the RF system, a pulse generator produces a radio frequency signal that is sent to the transmitter coils. The radio frequency pulse is responsible for the nutation of the bulk magnetization vector M that we learned about in a previous lecture. It is made up of both the electric and magnetic field components, with the magnetic components having a magnetic field designated as the B1 field. Once the RF pulse causes the bulk magnetization vector to nutate, it produces a transverse magnetization vector M subscript X that begins to relax. During relaxation, it emits a radio signal called the free induction decay signal. The FID or free induction decay signal is detected by the receiver coils and passed on to amplifiers and then to the computer system for processing. This slide lists a few radio frequency coils. Coils labeled as TR are transmit and receive coils, while PA coils are phased array coils. There are also coils labeled as quadrature or quad coils. Phased array and quadrature coils involve acquiring the FID signal with multiple surface coils to increase the signal strength and enlarge the field of view. TR coils transmit the B1 signal that nutates the bulk magnetization vector and also receive the FID pulses that result from the relaxation of the transverse magnetization M subject X as it decays to equilibrium. On the next slides, we shall look at some images of volume and surface coils. There are 4 volume coils shown on this slide. There is a foot and ankle coil, a breast coil system, a knee coil, and a wrist coil. Volume coils produce more uniform images than surface coils. Surface and flexible coils are shown on this slide. The uniformity of a surface coil is poorer than that of a volume coil because of more intense areas near the surface of the coil compared to anatomy farther away. Multi-purpose flex coils can also be used to perform volume imaging when wrapped around the anatomy. In this case, the uniformity is as good as a rigid volume coil. Before we get into MRI localization, let me review for you how we localized in radiography and CT. In radiography, localization was done by simply reading out the locations of the deck cells on a digital detector matrix, and the signals in those deck cells were mapped onto a two-dimensional matrix for display. In CT, localization is done by first filtering the ray projections received by the detector and back projecting the signals onto a two-dimensional matrix. The difference in linear attenuation coefficients along each ray was used to create Hounsfield unit maps on a two-dimensional matrix. In MRI, spatial localization is done by 3 gradients built into the machine. These are a slice select gradient, a phase encode gradient, and a frequency encode gradient. These images show the orientation of the various gradient coils relative to the bore of the MRI system. The X gradients are the top coil, the Y gradients the middle coil, and the Z gradients are the bottom coil. The net gradient is the vector sum of the 3 gradients as shown by the formula. The process of slice selection involves the application first of the gradient, followed by the RFB1 pulse. For axial MR images, the slice select gradient is applied along the Z-axis of the body. Under the influence of the gradient, the proton precessional frequencies in the volume are increased or decreased dependent on their distance from the null. The null point is the point where the net gradient line intersects the B0 field. The image here shows the gradient line with the B0 field and the location of the high and low frequency precession protons in the field. A slice select gradient localizes the position along the Z-axis of the patient if the axial slices are desired. For sagittal slices, slice select gradient is applied along the X-axis, and for coronal slices, slice select gradient is applied along the Y-axis. I will talk about this some more in a few slides. Once a slice is selected, the slice thickness is chiefly determined by the bandwidth of the radiofrequency pulse and the gradient strength across the field of view selected. The images shown here describe the process of slice thickness selection. For a fixed gradient strength in figure A, the slice thickness is determined by the bandwidth. A narrow bandwidth produces a thin slice, and a wide bandwidth produces a thick slice. For a fixed bandwidth, the slice thickness is produced by varying the gradient strength. A strong gradient produces a thin slice, and a weak gradient produces a thick slice. After the slice select gradient and following a brief interval, the phase encode gradient is turned on. The phase encode gradient localizes the Y position of voxels in the patient. After the phase encode gradient is turned off, all protons revert to the Larmor or resonant frequency, but are phase shifted linearly based on the specific gradient strength and polarity. The image shows a transverse slice of the patient with particular phase encode gradient strengths and the phase shifts produced as a result of varying the phase encode gradient strength around the positive and negative poles. Incremental positive phase change is introduced for protons under the positive pole, negative phase change under the negative pole, and no phase change occurs for protons at the null of the phase encode gradient. Throughout the acquisition sequence, the phase encode gradient strength and polarity are incrementally changed to introduce specific known phase changes as a function of position across the field of view for each acquisition interval. The figure shows 256 phase encoding changes. Keep the number 256 in mind when we look at frequency encode gradient on the next two slides. The frequency encode gradient is the third gradient applied. It is applied along the x-axis and in the same plane as the phase encode gradient. Both are perpendicular to the slice select gradient, which is applied along the z-axis. Frequency encode gradient is also called the readout gradient. After the frequency encode gradient is applied, the echo is detected by a receiving coil and stored in the computer for processing. The echo data containing frequency and phase information is Fourier transformed to convert frequency into spatial position. We shall look more closely at the frequency encode gradient next. In CT, the tube and detector both rotate about the patient to generate data projections that are used for creating the CT image. In MRI, projections can be created by rotating the frequency encode gradient about the patient as shown in the figure on this slide. A frequency encode gradient is applied in the x-axis, a phase encode gradient is applied along the y-axis, while a slice select gradient is applied along the z-axis. By rotating the frequency encode gradient about the z-axis, a set of projection data is obtained, filtered and back projected to create a tomographic image of the xy plane. On this image, only 8 frequency encode gradient projections are shown, but if we applied 256 frequency encode gradient steps, then together with the 256 phase encode gradient steps I mentioned 2 slides back, we shall now have 256 phase encode gradient and 256 frequency encode gradient steps for an acquisition matrix of 256 by 256. A complete pulse sequence is now shown on this slide with the radiofrequency excitation pulse applied first, followed by a slice select gradient, phase encode gradient, and frequency encode gradient. The echo pulse is read out at the same time as the frequency encode gradient signal. So to get a complete picture of the acquisition process, suppose we selected a 256 by 256 matrix for acquisition for a particular slice located along the z-axis of the patient. We will first apply the slice select gradient to locate the desired slice, then apply the phase encode gradient 256 times and apply the frequency encode gradient 256 times to get a 256 by 256 matrix. For each row of phase encode gradients data, 256 frequency encode gradient columns are applied and the echo detected. This is one signal. This process can be repeated up to 4 times and the signals averaged. If the process is repeated 4 times, we have 4 signal averages. The next phase encode gradient row is selected and 256 frequency encode gradient columns applied and several signals averaged. The whole process of phase encode gradient row, 256 frequency encode gradient columns, echo detection, repeating for several signals and averaging is repeated based on the repetition time TR until 256 frequency encode gradient columns have been applied to all 256 phase encode gradient data rows selected. The slice select gradient will then be changed to select the next position along the z-axis of the patient and the whole process repeated with the frequency encode gradient and phase encode gradient. This will be done until the pre-selected slice volume and slice thickness of the patient is acquired. The acquired data is processed and displayed. This whole process can be done to generate axial, coronal, sagittal or oblique planes by energizing the appropriate gradient coils and during the image acquisition process. Because the slice select gradient determines the orientation of slices, if you want to generate axial slices, the slice select gradient is applied to the z-axis coils. For coronal slices, the slice select gradient is applied to the y-axis coils, and for sagittal slices, the slice select gradient is applied to the x-axis coils. Oblique plane acquisition depends on a combination of the x, y, and z-axis coils energized simultaneously. Regardless of the orientation of the slice select gradient chosen, the phase encode gradient and frequency encode gradients are always perpendicular to the slice select gradient. On this slide, we shall calculate the acquisition time for a volume of tissue. Acquisition times are based on the number of echoes averaged or signals averaged, number of phase encode gradient steps, and the repetition times TR used. Acquisition time TA is equal to the product of signal or echo averages NA, number of phase encoding steps N subscript P, and repetition time TR. Let's look at an example. This formula tells us we can change acquisition time by changing either the number of signals averaged NA, the number of phase encoding steps NP, or the repetition time TR, or combinations of all three. Notice that all three factors act linearly, so changing any one of them will change the acquisition time proportionally. In this example, our acquisition time is 5.76 minutes. Suppose we cut the phase encode steps in half by going from 256 to 128. That will cut the acquisition time in half. Often, a simple way to reduce acquisition time is to place the phase encode gradient along the short axis of the patient so that fewer phase encode gradient steps are needed to acquire an image. Images can also be acquired in 3 dimensions by using a broadband RF pulse to excite a large volume of protons at the same time. In this case, 2 phase encode gradient steps are applied before the frequency encode gradient. The acquisition time formula from the previous slide is modified to include the 2 phase encode gradients as shown on this slide. We can now look at data collection and processing. Echo signals collected during the application of the frequency encode gradient are deposited in a 2-dimensional complex mathematical space called K-space. This space allows encoding of spatial frequencies as positive and negative complex numbers. The center of K-space is the zero spatial frequency signal as shown on the image. The 2D Fourier transform used for image processing enables us to transform signals between frequency space and phase or coordinate space. An inverse Fourier transform allows us to go back to the previous space. When filling the K-space data, lower frequencies are in the center and higher frequencies are in the periphery. The lowest amplitude signals are amplified logarithmically before being processed and displayed. Image D on this slide shows that most of the image content is in the center of K-space where the low frequencies are concentrated. An inverse Fourier transform converts the frequency information into grayscale information for display. This is image B on the slide. It's a 256 by 256 matrix. Let's now look at how the K-space is filled. K-space data can be filled sequentially or non-sequentially. When K-space data is filled sequentially, it is filled in a zigzag pattern shown on this image. Some sequences used for fast imaging applications like single-shot spin echo EPI use this method of filling K-space. Also, the gradient echo EPI method also can use sequential K-space filling. K-space can also be filled non-sequentially as shown on this image. These methods enhance signal, contrast, and achieve rapid scan times. The centric method fills the central rows first and the outer rows last. The keyhole method fills the outer rows first and the central rows only when the contrast appears. Spiral filling starts at the origin, which is the center of the K-space, and spirals outwards. This method requires an additional post-processing to regrade the data in a rectilinear matrix for the 2D Fourier transform processing. Propeller is another method of filling K-space, which stands for periodically rotated overlapping parallel lines with enhanced reconstruction. In this method, the rectangular block of data is acquired and then rotated about the center of K-space and another block acquired. This is shown in the bottom image. Let's finish up with a few questions. First question, which of these coils will be used for adjusting the homogeneity of the static B0 magnetic field? Your choices are: first choice, RF coils; second choice, gradient coils; third choice, Shimming coils; fourth choice, superconducting coils. The correct choice is Shimming coils. Next question. Which of these coils will be used for spatial localization in an MRI system? Your choices are: first choice, RF coils; second choice, gradient coils; third choice, Shimming coils; fourth choice, superconducting coils. The correct choice is gradient coils. Next question. An MRI of the head is acquired with 256 phase encoding steps, 3 signal averages, and a repetition time of 450 milliseconds, resulting in an acquisition time of 345.6 seconds. What is the new acquisition time after the number of signal averages is cut by 1/3? Your choices are 1036.8 seconds, 38.4 seconds, 1.92 minutes. Because we are cutting signal averages by 1/3, the total acquisition time originally given will be cut by 1/3, so the correct choice is 1.92 minutes or 115.2 seconds. This is the last slide. Thank you for watching this presentation.